Okay, looking at my circuit, I've replaced power supply A with the short wire or the short circuit to ground, that is the wire. I've reconnected power supply B, and I'll measure the voltage across it so that we verify that it is in fact 6 volts. And well, 6.01, we're 100th of a volt off, but I'll learn to live with it. There again, we need to mark the polarities of the voltages coming in. I'm going to use the same polarity, and what we'll find out is, because now that the power supply is over there, if I measure V1 this way, now I get a minus 1.63. So it is the reverse voltage that I got when I measured it with the power supply A connected. When I measure voltage 2, it too is a minus. So that's minus 4.37. And voltage 3, or the voltage cross resistor 3, is now, again using the same polarity, 1.63. Okay, so again I will record those voltages in my table. I've put in the voltages using the same polarities that I measured, because I use the designated plus and minus sides of those resistors. So we've got a minus 1.63. When we add that to 4.81, we know that when we add a negative number, that's subtraction. So I get 3.18. I have 7.19 minus 4.37, so I get 2.82. And then 7.19 plus 1.63, so I get 8.82. Now I will connect the original circuit, and we're going to measure what really happens when we have both supplies connected. Okay, I have reconnected both power supplies now. Notice that I took out the wire that was shorting out power supply A, so I place it back in position. I can go back and measure those two voltages. So we've got, from ground to that point, we've got 12 volts. From ground to that point, we've got 6 volts. So my 6 volt and my 12 volt are back in place. Now I'll go through and measure the voltage that I calculated by using my partial solution, that is the contributions from A separate from the contributions for B. So now with both A and B in position, I get 3.18. Again, keeping the same polarity, I get 2.81 and 8.82. When I look at the computed values, or the values that I computed, adding those two voltages together, we're off only a little bit in one of them. So we got 3.18, 2.81, so we are 100th of a volt off for the second measurement, and then 8.82, which again is right on the money. I'll now go through and calculate the variation for those percentages and talk a little bit about that. Okay, and so here I've got the table filled in. Table 11.1, you notice I've filled in the measured values for the voltages for R1, R2, and R3. Then I calculated the percentage. The percentage is based on the measured value minus the calculated value, or the calculated value minus the measured value, rather, divided by the calculated value. And so we have exactly the same for resistors 1 and 3, so they were 0% variation. The middle measurement was off by 100th of a volt. That 100th of a volt translated to 0.35%. So we're pretty much right on the money with all of those. Any variation percentage probably is based on round-off error, either due to the meter or to my calculation. Okay, now the next part of the experiment, and this is step 8, says we're going to build this circuit. This circuit is exactly the same as the other one. The only thing we're going to do is reverse power supply A and power supply B. And as part of those steps that we went through, we identified the plus and minus voltage on each resistor. We just designated which way we thought they'd be. I chose to use exactly the same polarity as I did the first time around. So it's plus to minus, plus to minus, and plus to minus. That probably, because these are reversed now, will end up with negative voltages, but that's kind of what I expect. I could have chosen any direction that I wanted to as long as I'm consistent throughout my measurements. The next thing that I'll do is reverse the two power supplies. In order to do that, I'll disconnect the black wires from what was the ground, the bottom of resistor 3. I connect the red wires up there because that's the direction those two are pointing. And then I just need to make sure I got the right one, connect the negative voltages up. So here's the same circuit that I had now with just the power supplies reversed, or the voltages on those power supplies reversed. So that means that if I, again, use that configuration to where this is power supply 2, that's 6.01, power supply, or A, is exactly 12 volts. So now I will go through and alternately remove one of the power supplies, replace it with a short to ground, take the measurements across each of the 3 resistors, and then calculate the overall value, and we should see essentially the same results since we're using the same components. I think I'll just go ahead and do that. You'll have to bear with me while I move wires around, but to remove first power supply B, replace the power supply with a short to ground, that is a piece of wire. Now I'll turn the power supply back on and go through and take my measurements. So as I take my measurements, again keeping the same polarity as I had before, I'll put the negative lead on the common. So the power in is 12 volts. The power across my A resistor then is minus 4.81. Let me write that down. The power, or the voltage across my second resistor, is minus 7.18. And my voltage across resistor 2, or 3, is 7.18, again negative. When I turn off the voltage, disconnect my short to ground, reconnect up voltage source 2, disconnect voltage source A, and connect this up to ground. Now I've rebuilt the circuit with only the second voltage source, VB, in place. So again, I'll start by measuring the power in, and we get 6.01 volts. The voltage across resistor A, again using the same polarity, is 1.63, so that's a positive 1.63. Across resistor 2 is 4.38, again positive, and the voltage across resistor 3 is a minus 1.63. Again, just because I had changed the power supplies. Let me just verify what I got here. That should be, yeah, minus. Okay, so I again have those same values. Now I'll put those into the table and do the. Okay, filling in the table, I've placed in my voltages. I've got a minus 4.81 plus 1.63 gives me minus 3.18. I have a minus 7.18 plus 4.38 gives me a minus 2.8, and then a minus 7.18 minus 1.63 gives me minus 8.81. Now I will connect up both power supplies and take the measurements again and see how we fare. Okay, with both VA and VB connected. Measuring VA, I've got minus 12, VB minus 6.01, and now I'll measure the voltage across resistor 1. I get minus 3.17. Voltage across resistor 2, minus 2.81. And the voltage across resistor 3, 8.82 or minus 8.82. And so looking at my table, we can see that we have a hundredth of a volt difference in each one of the measurements. I'll calculate the variation the same way. And basically my conclusion is that the superposition theorem works, that we can calculate the overall effect of having two voltage sources in a circuit by calculating the contribution to each separately, or in this case we measured them separately, then adding those two contributions together and we get the overall effect on the circuit.